Hi, and welcome to Quantum with Shantum, episode 1+0i. You already know. I'd like to start by saying thank you for your supportive comments and encouragement. I'm really happy that you're enjoying this, and I hope you continue to participate in this communal endeavor. Shout out to Hawk, by the way, who actually attempted the practice problems. And I'd like to say that I'd also love to see your solutions or, talk about it in office hours. Let's see what we have for today. We're going to talk about numbers. Okay, we're going to talk about numbers and how to represent numbers. So let's begin with something as old as counting sheep, and that is the set of natural numbers, okay, represented by n here. Natural numbers is the set of numbers we all know: 1, 2, 3, 4, and I know how to keep going, right? And every time we think about these sets of numbers, we're also going to think about some mathematical operations, such that when I apply those mathematical operations to numbers in this set, I'm either going to get a number that is in this set or not in this set. If I am in this set, I'm going to say it is closed under that operation. If I'm not in that set, I'm going to say I'm not closed under that operation. Okay, so the mathematical operation that the set of natural numbers is closed under is, to begin with, addition, because if I add 2 and 3, I'm still in the set. If I add 4 and 3, I'm still in the set. And scalar multiplication. If I multiply any two numbers, I'm still in that set. And every time we think about these mathematical operations that make it are such that they're closed under that, such that the sets are closed under those mathematical operations, we're also going to think of operations that make it such that it's not closed. Okay, and one such operation is subtraction. And I can also represent these operations in the form of a polynomial equation, right? So what I'm saying is, let me take a number x, which is a natural number, and subtract x. So this is a polynomial equation, right? And subtract x. What do I get? Well, I don't know. I'm not in the set, right? I don't know. And so let's be nice and include 0. And that makes the set of whole numbers, okay, represented by W here. Whole numbers include the 0 and all the natural numbers, right? This set encompasses all of the natural numbers and includes 0. And this is again closed under addition and multiplication. All right. And the operation this is not closed under is again subtraction, but this time x minus x is defined. So what I'm going to have to subtract here is at least x minus x plus 1. What's the value? For example, what if I take 1 and what if I subtract 2? Well, I don't know. I'm not in this set anymore. Okay. And the set of numbers that is closed under subtraction is known as the integers, okay, represented by z here. So z is the set of integers, and it goes from all the way from negative infinity to includes 0 and all the way to positive infinity. Okay, and the operations that this set is closed under is addition, multiplication, as well as subtraction. Now let's concoct a mathematical operation such that it's not closed under in this set. It's not closed. The set is not closed under that operation. What is that going to be? Well, it is division, right? So let me think of a polynomial expression that suggests division. Let me take 2, which is an integer. Let me take x, which I want to find if it is in the set or not, and subtract 5 equals 0. That implies x is what? Well, I don't know. I'm not in this set anymore. Okay, we don't know fractions yet. And the set that is closed under division includes the fractions, is called is called rational numbers. I'm getting ahead of myself. It's called rational numbers. Okay, so Q is the set of rational numbers, and they can be written in the form of fractions. And the fraction is looks like this: P over Q where P and Q are integers, right? And Q cannot be the integer known as 0 because, well, I'm dividing by it, okay? And the operations, the set of rational numbers is closed under is addition, subtraction, multiplication, subtraction, as well as division, okay? And as always, I can concoct a mathematical operation or a polynomial such that it is not going to be closed under this set, which is, and I can cheat here because I know a number that is not rational, I know a number that is irrational, and let's make a polynomial with that as its solution, and that can be the polynomial x squared minus 2 equals 0. Okay, the solutions to this are x equals either plus square root of 2 or minus square root of 2, neither of which has a representation of the form p over q, where p and q are integers. Okay, so what is this? I don't know. I'm not in this set. The set of numbers that also includes irrational numbers is going to be called real numbers. Okay, so real numbers encompasses all of these numbers as well as irrational numbers, real numbers with the R. Now, real numbers are closed under operations plus, multiplication, subtraction, and division. And let's go on a little tangent here. Let's go on a little tangent here to explore something interesting. Okay. See how when I first said this is the set of natural numbers and all the other numbers that come above it also encompass the down below, but the set of natural numbers is infinite. The set of natural numbers is infinite, and the set of integers is also infinite. So what does this mean? Some infinities are bigger than other infinities. Okay, this is the nature of infinite sets. The set of natural numbers is infinite, but simply because of the virtue that the set of integers, for example, encompasses all of the natural numbers, and that set is an infinite set, that infinity is bigger than the set of natural numbers, than the infinity represented by the natural numbers. So very interesting. Some infinities, wow, some infinities are bigger than others. How cool is that? Okay. And let's get back from our tangent here. And where were we? We were about to concoct an operation, a mathematical operation, or analogously, a polynomial, such that it is not closed under, or the set of real numbers is not closed under that operation. Okay. And that polynomial turns out to be, and I can cheat here because I know a number that is not real, and that equation ends up being x squared plus 1 equals 0. Okay, if you try to solve this, you get x equals, well, I don't know. I'm not in this set anymore. Okay, and so the set, finally, the set, where's my mouse? Oh, the set of numbers that is closed under, I mean, let me first mention that what did we just do here? We attempted to take the square root of a negative number, right? And so this is closed under addition, subtraction, multiplication, division, but not the square root. Okay, so the real numbers, the set of real numbers is not closed under the square root, but the set that is closed under the square root is going to be called the complex numbers. Okay, so complex numbers can satisfy this equation as well, or in other words, it is closed under all these operations as well as the square root. But there's a nice theorem that says the set of complex numbers is closed under all operations. All right, how cool is that? And how they define this is by defining the square root of -1. And they say the square root of -1 is this number called I. Okay, and we're gonna delve deeper into this stuff, complex numbers. But first, let's really see what this guy is trying to say. The equation x squared plus 1 equals 0. What is this equation trying to say? This equation is trying to say x squared equals -1. Okay, this means find me a number such that when I multiply by itself, I get -1. Okay, find me a number such that when I take a square of it, multiply by itself, I get -1. Now, let's first learn how we can multiply numbers. But to do that, we need to know how to represent numbers, okay? So this little fun fact here, and this very important fact actually, is that real numbers are isomorphic. Okay, I'm going to define what that term means. Real numbers are isomorphic to vectors in R, this vector space known as R, okay, which is the real numbers as well, by the way. There's a kind of a double implication. So real numbers are isomorphic to vectors in R, and what isomorphic means is that this is a type of mapping. This is a type of mapping that preserves the mathematical structure, okay? And in other words, I can go back and forth between these two representations. I can think about real numbers as what I've always been thinking about, just numbers, but I can also represent them as vectors in R, okay? In other words, let me represent the line of real numbers, okay? This is where all the numbers live, increases this way. This is where all the numbers live. This is R. And let me locate 0 here. And if I were to say represent the number known as 1, what do? I use this fact that they are isomorph, that the real number 1 is isomorphic to a vector in R. And what is a vector? A vector is a quantity that has magnitude. So in this case, the magnitude is 1, but also a direction. So that 1 is not on the negative side. It's not directed that way, in the -1 way, but it is directed towards the positive axis. Okay, this is where we increase. So this means this is how I represent the number 1. Now, all the while, let's keep in the back of the mind, what do we want? We want a number such that when I multiply it by itself, I get -1. Okay, so now let's think of what happens when I multiply numbers in this representation. So let's see what multiplication does. Multiply by a positive number. This is how I'm going to write positive. Multiply by a positive number. What happens when I multiply by a positive number? Let's say that number is 2. If I multiply 2 by 1, I get a quantity known as 2, which can be represented with this vector now. All right, this is probably where I get to use this. This can be represented now by this vector. 2 is going to be represented by this red vector. But all we need to keep in account is the change in magnitude and the change in direction, right? Because we're talking about vectors. Surely the magnitude changed because you multiplied it by a number other than 1. Surely the magnitude changed, but the direction was preserved. So if you multiply by a positive number, what did we note? Direction is preserved. Direction is preserved. What happens now when I multiply by a negative number? Let's use our vector 1 as an example. When I multiply 1 by, say, now -2, what do I get? I get this blue vector, -2. This blue vector which represents -2, which is directed the other way. Of course, its magnitude changed because I multiplied it by a number that was different from 1. But the other thing to note is that when I multiply by a negative number, what happens? Direction changes, and I can also talk about it as a 180-degree counterclockwise rotation of that vector. What does that mean? That simply means I have changed the direction, right? 180 degrees, which is all the way here, counterclockwise, go that way, sure, why not? Counterclockwise rotation of that vector. We started out with 1, and multiplying by a negative number changed its direction. How? 180 degrees counterclockwise rotation. All right, so that's nice. Now that we know how to multiply numbers, let's first see why the operation square root of 2 is not closed under real numbers. Okay, let's take any real number, and let's see why taking the square of it, right? Taking the square of it will never give you a negative number. Let's see why. Because now, if I take a number which is already negative, take a number which is already negative, which I'm going to represent it like that, an arrow pointing that way, and multiply by itself. Multiply by itself. So multiplying by a negative number, and all I need to know is that number is negative in order for me to figure out what happens to the overall direction. If I multiply that negative number by a negative number by itself, I get a positive number. Why? Because multiplying by a negative number requires me to do a 180-degree counterclockwise rotation of the vector. In other words, change the direction of the vector, so I will always get a positive number. And if I take a positive number and take the square of it, I will preserve the direction, meaning I started with the positive, so I will still be a positive number. I'm always going to get a positive number when I take squares of numbers in the real number. Okay? So, how can we ever think about a number such that when I multiply by itself, I get a negative number? In fact, I know the magnitude of that negative number as well. It's 1. Okay. How do I find this number such that when I multiply by itself, I get -1? Let's see what that really means. And we already said that how complex number is defined is that they defined that I don't know if you can see this, square root of -1 is I, right? That's how they defined it. And they said square root of I is -1, or rather I is square root of -1. I is square root of -1. This means I squared is equal to -1. Okay, I'm just taking the square of both sides. All right, I squared is going to be -1. Now, what does this mean? This means take a number 1, multiply it by I, multiply it by I again, I get -1. Isn't that what it means? I can always multiply this equation by 1 on both sides, which gives me 1 times I equals -1 times 1, which is -1, right? Now, what does this mean? Let's see what this means. This means take my vector 1, right? That's my number 1. Take my vector 1, okay? Take my vector 1. That's my vector 1. Multiply it by I, multiply it by I again, and you are going to end up, this equation says, you are going to end up here to -1. Wow. What does that mean? So far we know multiplying by a positive number, same direction. Multiply by a negative number, 180 degrees rotation, counterclockwise. Multiply, and what does this equation say? I take the vector I, multiply it by something called I, then multiply it by something called I again, then I reach the 180-degree transformation. So what does this mean? This means I need a number which is somewhere in between, such that when I take 1 and I apply this transformation, which is known as multiply by I should get here. I should reach here. My vector should be rotated like that, right? This is by multiplying by I. When I multiply by I should actually change my change the angle of my vector by 90 degrees. So why? Because when I do that again, right? When I do that again, I'm gonna end up at -1. I'm gonna make another 90 degrees rotation counterclockwise, and I'm gonna end up here. Wow. So what does this mean? This means I is a number, all right, but it does not live on the real axis. Not only that, where does it live? It lives perpendicular to the real axis. It lives in a lateral dimension to the real axis, okay? The imaginary numbers live here. This is where they live. What does that mean? And knowing that complex numbers is the entirety of representation of numbers, what does that mean? This means numbers are two-dimensional. Wow. This means numbers are two-dimensional, okay? And this is a crazy revolutionary understanding in mathematics, and that's why there's also a theorem associated with it, okay, so-called the fundamental theorem of algebra. So let's see what that says. Fundamental theorem of algebra says that the the set of complex numbers, the set, actually, I'm going to use a word which I haven't defined yet, but the people taking group rings and fields are going to enjoy this. The field of complex numbers, right? The field of complex numbers, represented by the C here, the field of complex numbers is algebraically closed. Algebraically closed. The field of complex numbers is algebraically closed. What does this mean? This means I can concoct any polynomial equation. I can concoct any and all operations and apply to this number called a complex number, and I am still going to end up with a complex number. I am closed under any and all operations. Okay, so that is what the fundamental theorem of algebra says. But because you need more than algebra to prove this theorem, this is neither fundamental nor a theorem of algebra. Okay, so that's a fun fact about this fundamental theorem. So going back to complex numbers now, complex numbers, we said, are two-dimensional, right? And by extension, because complex numbers are all numbers, numbers are two-dimensional, and a real number, which we've always known as, which are all the numbers we've always ever known, are just complex numbers with their imaginary part equal to 0, right? In that lateral dimension, no values in that lateral dimension. So let's think about this more deeply. Complex numbers are two-dimensional, and therefore, okay, complex numbers are isomorphic to vectors in R2. Remember how we said real numbers are isomorphic to vectors in R? Just like that, complex numbers are isomorphic to vectors in R2, once again, meaning I can talk about complex numbers as being vectors in this two-dimensional vector space and go back and forth between those representations. All right, so let's see how we can represent a number then? How I can represent a complex number? Any other number which you know known as real number is again a complex number with imaginary part equal to 0. Okay, so how can we represent numbers? We can represent numbers in this two-dimensional plane because they are two-dimensional, and because of this fact that they're isomorphic to vectors in R2, not only do I represent these as points in the two-dimensional plane, but I represent them as vectors in this two-dimensional plane. Okay, so a complex number which has, let's say it's x-axis here and y-axis here, and I'm going to label this axis x as real, one-dimensional real, and the other perpendicular direction. You remember how the multiplication by I prompted us to concoct another dimension so as to make sense I squared equals -1. This dimension is going to be called imaginary. And I very much prefer the term lateral because it's not literally imaginary. Okay, these very much have real existence. And this point was my point in this two-dimensional plane. And how do I represent a number? It's a vector. It's a vector from the origin to that point. Looks like that. Okay, and as always, a vector has two components. Earlier we only had one component, and that was it for us. But now, because this is a vector in two-dimensional space, we got two components. One is called the y component here, and the other is called the x component here. Okay, and we can also talk about the length of this vector. Okay, the length of this vector I'm going to represent as r. The length of this vector, and it's going to be clear why I'm using r. The length of this vector is going to be what? If I do this, take this triangle and use the Pythagoras theorem, that's right, it's going to be square root of x squared plus y squared. Right, I'm going to get something called r squared equals x squared plus y squared, and I know that r is non-zero, or rather r is positive in this case because I'm talking about a magnitude, I'm talking about a length, right? And so that positive non-zero value is going to be square root of x squared plus y squared. Now, vectors in R2, right? Complex numbers, sure, are vectors in R2, but vectors in R2 themselves can have multiple representations. This representation is known as the Cartesian representation, okay? We can convert this Cartesian representation to the polar representation. Guess why? Because that's isomorphic as well, okay? And this is the Cartesian representation. And now if we move on to the polar representation, which is going to be very important when dealing with complex numbers, is we're going to have to define, just like in the Cartesian plane, we defined 2 degrees of freedom, x-axis and y-axis. Here we're going to define 2 degrees of freedom, known as, one is called the distance from the origin, which is aptly named r. Okay, one is called the distance from the origin. So how do I represent this vector? One, by using r, the distance from the origin. And the other is the angle that it makes with the positive x-axis measured by increasing values counterclockwise, called theta. Okay, so this angle, which increases counterclockwise, which is with respect to the positive x-axis here, is the second variable we need to define a vector in R2. So we need polar coordinates r and theta. Okay, just like we needed x and y in Cartesian, we need r and theta in the polar coordinates. Now, we can use, once again, the Pythagorean theorem expanded to talk about sines and cosines to say that x in the Cartesian representation is what? R cosine theta. Y is r sine of theta. All right, and how do I write a complex number? I write the complex number here as x plus yi. Okay, the complex number here is x plus yi. This vector can be represented as x plus I y, because I have x units in the x direction and y units in the I direction, right? Remember, this is imaginary axis. So this is the x plus iy, which is the Cartesian representation of this vector. And the polar representation of this vector, well, is going to be what? It's still going to be x plus iy, but how is x plus iy going to be written? X plus iy is going to be written, and these three signs means that it's an identical expression. X plus iy can be written as r cosine of theta, because now I'm only going to use polar coordinates, meaning I'm only going to use r and theta. X plus iy is going to be r cosine of theta plus I times r sine of theta. All right, and this Euler showed, okay, Euler, famous mathematician, showed that this can be written as r times e to the I theta. Okay, so this representation in the Cartesian plane, x plus iy, can be represented using polar coordinates as r e to the I theta, where r e to the I theta can be expanded as r cosine of theta being the real part of this complex number, and r sine of theta being the imaginary part, because it's multiplied by I, okay, being the imaginary part of this complex number. Awesome. So now we know how to represent numbers. Numbers are what? Isomorphic to vectors. Real numbers are isomorphic to vectors in R. Complex numbers are isomorphic to vectors in R too, right? And so this is how we would represent numbers. Let's do a quick example here. How do I represent the number known as 1? That's the name of the episode, right? 1 is also known as 1 plus 0i, right? 1 is a real number with its imaginary part being 0. And how do I represent something called x plus iy? Well, I first find r e to the I theta, right? That is what it is. It is r e to the I theta. So I need r. And what is r? R is the length of the vector, magnitude of the vector, which is given by the expression square root of x squared plus y squared. So let's do that. Square root of x squared plus y squared times e to the I theta, right? R e to the I theta times e to the I theta times e to the I theta. But now I need to know what my theta is. What is theta? Well, theta, how did we define theta? Theta is the angle from the positive x-axis increasing counterclockwise, right? Where is my vector r? Where's my vector 1? My vector 1 in the complex plane looks like this. This is y imaginary, this is x real, and my number known as 1 is a vector in R2, which looks like this, right? I'm going to call this 1. So what's the theta with respect to the x-axis? Well, it is parallel. This vector is parallel to the x-axis. Therefore, theta is going to be 0. Okay, theta is going to be 0. And therefore, this number can also be written as square root of 1 squared plus 1 squared, which is 1. E to the I0 is what? E to the I0 is what? R times e to the I0. If I factor out r here, it is cosine theta plus I sine theta. And cosine theta is cosine 0 plus I sine 0, which I get 1. Cosine of 0 is 1 plus I times sine of 0 is 0. So this is going to be, at the end of the day, 1. And 1 better equal to 1. Okay, so we just went through Cartesian and polar representations and showed that it's consistent. So that is how I would represent 1 using the polar way. This is how I would represent using 1. It is square root of 1 plus square root of 1, which is 1, times e to the I0. But you will notice that the angle that satisfies this vector 1 is not just 0. Okay, of course, I have 0 degrees with respect to the x-axis, but I also have an entire circle 2 pi angle with respect to the x-axis, right? This vector also has angle 2 pi with respect to the x-axis. So I can write 1 as square root of 1 square plus 0 square root of 1 times e to the I, not just 0, but also 2 pi. Okay? And not only that, I can also write it as 4 pi, because I can go 1 more times around the circle. and still have the same vector, the same angle. Okay, so I can represent 1 then as generally 1 times, because that's the magnitude, right? Square root of 1 squared plus z squared, square root of 1 is 1, which is the magnitude of the vector 1 times e to the I theta, but theta can be not just 2 pi, but any multiple of it. So I'm going to write it as 2 pi times any multiple of it, k, where k is an integer. Okay, and why am I saying integer and not natural numbers? Well, if k is -3, that means I go around this circle 3 times, but in the opposite direction, still the same thing, right? So this is how I would represent 1. Awesome. Now, let's see what this curious complex number. Now let's go back to trying to represent e to the i's into the numbers we know. Okay, into the Cartesian plane. Let's look at this curious complex number, e to the I pi. Okay, e to the I pi. And how do I know it's a complex number? Because it fits this form. Because it fits this form r e to the I theta, where r is 1, right? It's 1 times e to the I theta, e to the I pi. And theta is what? R e to the I theta. Theta here is pi. So how do I represent this complex number? How do I represent this complex number? I can write it as how it fits in. I can write it as how it fits with the formula. It's 1 times e to the I pi, first of all. It's 1 times e to the I pi. Then I'm going to try to graph this complex number because I know how to write a graphical representation of it. This is the x-axis, this is the y-axis. And this says, find a complex number with magnitude 1. Sure, I can make a vector with magnitude 1. But also the direction of that vector is defined by the angle pi. The direction of the vector is defined by the angle pi. And how did I define theta? I define theta by saying it is measured with respect to the positive x-axis and it increases counterclockwise. So how do I go from 0, which is here, to pi? Well, I go, pi is half of a circle, so I go here, right? I go here, and what's the magnitude of my vector? It's 1. So I am 1 unit in this direction, 1 unit in this direction, and this vector is known as, or rather this number is known as -1. Okay, so e to the I pi is equal to -1. And conversely, or rather this implies e to the I pi plus 1 equals 0. Wow. This is the Euler's identity. Okay, this is also known as the Euler's identity, e to the I pi plus 1 equals 0. We by no means proved it. We just learned to visualize complex numbers in a graphical representation. And actually, yeah, we do agree that the complex number e to the I pi represents the real number -1. Wow. And with that, I'm going to leave you with a quick extra credit problem. Okay. And this is going to be fun because here we verify that the field of complex numbers is algebraically closed. We verify the fundamental theorem of algebra here. And by showing that, well, the field of complex numbers, the set of complex numbers is closed under square root. Okay, so let me take the square root and let me take a complex number called I. And if I can show that this quantity, whatever that is, square root of I, is in complex numbers, this means this is an element of the set. If this quantity square root of I is an element of the set C, then what happens? Then I know that then I've verified the fundamental theorem of algebra. Okay, I would also like you to evaluate this and find your answer in Cartesian coordinates. Okay, and find in Cartesian coordinates. And how do I do this? My hint here is that first represent I First, represent I as r e to the I theta, a complex number in polar coordinates. Then do the square root, apply square root. How do you apply square root? It's the same as saying raise the power of a something by half, right? And then, because I said find in Cartesian coordinates, and because of the fact that polar representation of a vector is isomorphic to the Cartesian representation of the vector, convert it back. Convert back to Cartesian. Okay? All right, this was a longer one than I'd expected, but a fun one indeed. Enjoy your time. Bye-bye.